More generally, we can look at what we call the representative elements versus the transition elements. So for this discussion, we're actually going to go across and number our groups or families. We said earlier there are 18 columns going across. So 1, 2, 3, 4. Not going to count all of them off for you here, but you get the general idea. And this is going to help us distinguish between what we call representative elements and transition elements. So this is a modern numbering convention here that you see just going across from left to right, 1 through 18, and that's the numbering convention that we are going to use for the columns on the periodic table. You will see some sources that have slightly different variations, and we'll talk about that in just a second, but we're going to focus in class on this very straightforward 1 through 18 numbering the columns from left to right to indicate the groups and families in the periodic table. So when we look at these columns, if we consider the first 2 columns in the periodic table and then columns 13 through 18 over here in the P block of the periodic table, so we are looking at the S and the P block elements. If you want to think about it in terms of the sublevels, quantum theory, these are what we refer to collectively as the representative elements. Now we do find within this group of representative elements that there are a wide variety of chemical and physical properties. But within this larger group of representative elements, there are a couple of groups of note that we should be familiar with. So we'll kind of go through in a different color here and talk about a few of these groups, starting with the first column. Over here, column number 1. These elements are metals, we saw earlier, with the exception of hydrogen. So hydrogen, sort of questionable as to whether or not it should be included in this group, depending on how you're going to categorize the elements, but it does have the same number of valence electrons as all of the other elements in the first group here. So that's a similarity. It is, of course, not a metal. It is a nonmetal. So in that regard, it doesn't fit with these group 1 elements. So if we look at everything except for hydrogen in that first column, so lithium down through francium or francium, depending on how you want to pronounce it, these are what are called the alkali metals. Alkali metals all have 1 valence electron, so their electron dot structures, if we draw one for lithium, have just 1 dot next to them. They're very willing to give up, to let go of that 1 electron and form a positive 1 ion, and as a result, the alkali metals tend to have extremely high reactivity, the most reactive metals on the periodic table. So the first group there, that first column, we refer to as the alkali metals. Let's take a look at another group, the next one over. Do this in a different color here. The second group, second column on the periodic table. These elements we refer to as the alkaline earth metals. Try and match the colors up here. So that is alkaline earth. Now, first of all, notice that this sounds a lot like alkali metals, but this is alkaline, I-N-E, not alkali, as we saw for the first group. The alkaline earth metals, if we look at one like magnesium, they all have 2 valence electrons. They're still pretty reactive, but they're less reactive than the alkali metals. It's harder to lose 2 electrons than it is just to lose 1. They still do tend to form positive ions. Positive 2 would be the charge on the alkaline earth metals when they form ions, but they're not as reactive as the alkali metals. The next group we're going to take a look at, we're going to skip all the way over to group 17 on the periodic table. So let's pick another color here. Go with orange, group 17. This group I'm going to leave astatine out because we talked about astatine earlier. We really don't necessarily know enough about it to truly include it in this group. Group 17 we refer to as the halogens. And they all have 7 valence electrons. So if we were to look at the electron dot structure for chlorine, it's going to be 7 valence electrons for chlorine. Halogens also tend to be highly reactive. Now they're nonmetals, unlike the alkali metals and the alkaline earth metals. These are nonmetals. So they will ionize by gaining electrons rather than losing electrons. But they only need to gain 1 in order to achieve stability. So it's, again, relatively easy for these atoms to gain a single electron to become -1 ions, and as a result, halogens tend to be fairly reactive as far as elements go and nonmetals are concerned. One more column, one more group that we want to look at here before we're all said and done with our discussion. Let's go with green for the last group here, and that's column 18, group 18 on the periodic table. These are what are referred to as the noble gases. So unlike the previous 3 groups that we talked about, noble gases are incredibly unreactive. It's not that they can't be made to react at all, but if left to their own devices, if given a choice, these are elements that are happy where they're at. They're fairly stable because they have a complete outer shell. That's one way that we describe that condition of having 8 electrons in the valence. So if you were going to draw an electron configuration for any of these other than helium, helium's an exception, but if we were to look at neon, neon's going to have 8 valence electrons. So it doesn't really want to gain any electrons or lose any electrons. It's stable the way it is. And that's why the noble gases tend to be very unreactive. Now, cleared out the page. That's all right. Can I undo that? Maybe? I don't know. Go back and pause it if you want to look at all that information again. I just want to mention real quick about helium. Helium is in that noble gas column. But it doesn't have 8 valence electrons because it's in the first period, it's in the first energy level, and we all remember that there is only one sublevel. It's an S sublevel. There's only one orbital in that sublevel. We only have 2 electrons, configuration of 1s2 for helium. So helium is going to have just 2 valence electrons. But for helium, that's as many as it can have, since its electrons occupy the first energy level with just 1 sublevel and 1 orbital. 2 electrons is the maximum. And as a result, this is a stable configuration for helium. So it does have characteristics similar to those of the rest of the noble gases. All right. So let's now take a look at those elements that are in the middle of the periodic table here. So columns 3 through 12. So we're ignoring now the S and the P block. That's what we looked at earlier with the representative elements. We're looking at the, get a highlighter here. Have the right color. Yeah, that's going to work. Looking at the D block of the periodic table. So these are elements who are currently filling a D sublevel in their electron configurations. One thing that we probably should remind us of, or remind ourselves of, about the D block elements is that when you are in the D block and you're filling a D sublevel, that D sublevel is always 1 energy level behind the principal energy level, or in other words, 1 energy level behind the period in the periodic table. So if we're in the 4th period going across, and let's get a different color here just for emphasis. Let's say we're looking at iron. We would have for potassium, this would be 4s1, calcium would be 4s2, but then when we get to the D block, this is now 3d1, 3d2, 3d3, etc. So because of the sublevel crossing that occurs on the Aufbau diagram, we do see that the D sublevel is actually 1 energy level less than the principal energy level, or in terms of the periodic table, one number less than the period on the periodic table. We see something similar with the inner transition metals. The inner transition metals are those elements that are part of the lanthanide and actinide series down here below the main portion of the periodic table. This is what we refer to in terms of sublevels as the F block of the periodic table. So these elements are currently filling F sublevels. And we do see that the F sublevel is actually 2 energy levels less than the principal energy level. So the first period on the periodic table in which we actually see these F sublevels is the 6th period. So over here with cesium, this would be 6s1, and then barium 6s2. When we get to the F orbitals, we do find that these are actually 4F orbitals in that row, 2 energy levels fewer than the 6 for the S and the P, and the 6 for the period on the periodic table. Similarly, the d orbitals in that 6th row would be 5d orbitals. Okay, so again, we see that the d sublevel is 1 energy level less than the valence energy level, and the F sublevel is 2 energy levels less than the valence energy level. Or another way of thinking about it, d is 1 number lower than the period or the row that the element's found in. The F is 2 numbers less than the period or the row that the element is found in. So anyway, let's go back to talking about groups 3 through 12 here just real quick, and then we can finish up for today's lesson. These are what are referred to as the transition elements. As you can see, and hopefully remember from our earlier discussion, all of these transition elements are metals. The elements down here in the lanthanide and actinide series, we like to specify these as the inner transition elements to distinguish them from the elements in the D block. Although many people will just say that all of those elements together could be called transition elements, this is again one of those things that will sort of depend on who you talk to, like we looked at with the metalloids. So we sort of discussed in class a little bit about how the number of valence electrons tends to be either 1 or 2 for these transition metals, depending on whether or not that element happens to be one of the Aufbau exceptions. For instance, if you look at nickel, nickel is going to have an electron configuration of argon 4s2 and then 3d8, so it would end up having 2 valence electrons. The 4s2 would be the valence. The 3d8 do not count as valence electrons because the d sublevel is 1 energy less than the valence energy level. Whereas if we were to look at copper, which is an Aufbau exception, so you might recall from our discussions in class in Chapter 5 that copper's preferred electron configuration is argon 4s1 3d10. So we promote one of those 4s electrons that's predicted by the Aufbau filling diagram to the d sublevel, and as a result, copper only has 1 valence electron. So we do see that some of the elements in the transition block have just 1 valence electron, others have 2. We also find that most of these elements can form multiple ions. So you think about copper. Copper has 2 common ions, copper 1, which is a positive 1 ion, and copper 2, which is a positive 2 ion. And we see similar, call them type 2 cations or type 2 behavior with some of the other elements in that transition block. And that's something that we'll talk about a little bit later on when we talk about ionic bonding. Okay, so that took a little bit longer than I planned on, but that is a general overview of the layout of the periodic table and some of the characteristics of the periodic table, and a little bit of information about how we can use the periodic table to start thinking about chemical properties of the elements, reactivity of the elements in terms of valence electron configurations.